Peptide bond formation is a condensation reaction. In other words, a reaction which yields water as a byproduct, as this slide shows. It is very important to note that there is partial double bond character to the peptide bond. X-ray data provides evidence, most clearly seen by the bonding angles approximating 120 degrees. X-ray data is a little bit more confusing in that the bond length makes it appear that both the carbon-oxygen and the carbon-nitrogen bonds are double bonded. At any rate, this partial double bond character leads to important structural ramifications as the peptide bond rotates as a plane, and therefore only certain rotations are permissible. We will have more to say about this in a subsequent section. Short polymers of amino acids are referred to as dipeptides, tripeptides, and so on. Dipeptide means that two amino acids are joined by one peptide bond. One of the biggest points of contention is when a peptide becomes a polypeptide or protein. The cutoff for most biochemists would be that 50 or more amino acids would represent a protein rather than a polypeptide. A dipeptide might be named something like glycyl alanine. As in organic chemistry, the YL indicates that glycine is covalently bound to alanine. I have a different dipeptide shown in the upper right part of this slide, and I would like you to come up with the name of it, and I will tell you shortly what it is. I will also note that I drew this structure incorrectly, as we talked about in section 2.3. There is not a pH at which the amino group is unprotonated and the carboxylic acid group is protonated. The tripeptide at the bottom right of this slide is shown drawn in its physiologically correct form. Although we could name this tripeptide, it has a common name of glutathione. Because of the importance of the sulfhydryl group in the function of this tripeptide, it is given the abbreviation GSH. This nomenclature system quickly becomes cumbersome. Therefore, the amino acid sequence is usually given in either the 3 or 1-letter abbreviations. For example, lyse, asp, glu, lu, or KDEL. Very importantly, by convention, we always name from the amino terminus to the carboxy terminus. In working with peptides, it is more useful to think about net charges than isoelectric points. A shortcut notation I use to quickly calculate the net charge is as follows. I draw a horizontal line to represent my peptide bond, or my peptide. Because at physiological pH, the amino group is positively charged and the carboxylic acid group, which we can call the amino terminus and carboxy terminus respectively, is negatively charged. I place a positive and a negative sign at each end of the line. Then, for each of the residues in the peptide, and I am going to use KDEL here, I give the charge at physiological pH, in this case positive, negative, negative, neutral. The amino and carboxy termini are always going to cancel each other out, so I've drawn a hash mark through those charges. In this case, the positive and negative of K and D cancel each other out, and the net charge of this peptide at physiological pH is -1. One of the reasons that the net charge is far more important than the isoelectric point is shown on this slide. The pK values for the carboxy and amino terminus of the amino acid alanine are 2.34 and 9.69. But if we have the dipeptide alanyl alanine, the experimentally derived pK values are 3.12 and 8.30. If we have a hexapeptide or longer, the pK values are 3.42 and 7.94. In other words, the pK values tend towards neutrality in peptides and proteins. Furthermore, the pK value can change depending on the environment. In this example, we stuck with a single amino acid, but if we have a positive charge next to a negative charge, that affects the pK value of both. This will become far more important when we start talking about proteins. But if we have a hydrophobic pocket inside the protein, the pK value has almost nothing to do with the pK value of a free amino acid. Peptides have physiological activity, and there are almost unlimited examples that we could use. For example, insulin is a peptide which has the physiological function of decreasing blood glucose values. Oxytocin is about 12 amino acids long and functions in lactating cattle to cause milk production. Interestingly, it was relatively recently been found that oxytocin increases during bonding between adult humans. Endorphins are about 6 amino acids or so and are released by the brain as natural painkillers. Life would not exist without peptides. Gonadotropin-releasing hormone, GnRH, causes the production of luteinizing hormone, LH, which causes eggs to be released from the ovary. And when pregnancy ensues, chorionic gonadotropin, HCG, maintains viability of the embryo before the embryo begins to produce its own hormone. By the way, the name of that dipeptide on one of the earlier slides was aspartyl phenylalanine.